All right, in this video, we're going to continue with 5.2 and I think 5.3. Wherever we are, we're at example 5.3 in the text, okay? So this example is going to introduce a notion of a confidence interval, and in particular, a bootstrap confidence interval through an example, and then in the next panel, I'll get more specific about what that actually means. All right, so we have a new data set that we're dealing with in example 5.3 called Bangladesh. And the data set contains the results of measuring arsenic levels in 271 wells in Bangladesh. Now, the average of those 271 arsenic levels is 125.31 parts per billion, and the standard deviation is about 298 parts per billion, which, if you think about it, is a huge standard deviation. We can't even go 298 units to the left at 125, or else we're in negative territory. So this is telling us that the data is really spread out, okay? So it's been determined that 10 parts per billion or less of arsenic is considered safe for drinking water. And so it's not looking good, right? And 57% of the wells of those 271 exceed that 10 parts per billion. So that also tells us the data is incredibly skewed right, because if 43% of the wells are below 10 parts per billion, but the average is 125.31. We must have a lot of things way down there with high levels of arsenic, okay? All right, and our goal is to calculate what we're going to call the 95% bootstrap confidence interval of the mean arsenic level, sometimes called the 95% bootstrap percentile confidence interval, okay? All right, well, some things to note. What we're going to see when we look through the data is that the data here is not normally distributed. But since our test statistic is going to be a sample average, the central limit theorem takes over and says that the sample averages distribution is approximately normally distributed, okay? So in red is the results of one push through of this simulation. So the actual values we get when we go through it on the screen are going to be slightly different. But once when I did it, I got the mean of the bootstrap distribution was 125.28 parts per billion. And if you note, that mean of the bootstrap distribution seems to be pretty much the same as the mean of the original sample, as we should have expected from our last few videos. And the standard error is much less at 18.28. Standard error is much less because now I'm looking at the distribution of X bar. So I'm dividing by 271, right? When I do a bootstrap distribution here, I'm going to resample 271 wells with replacement from the original 271. Test statistic is going to be the sample average. So I'm going to be adding those and dividing by 271. And when I calculate the variance, I can drag that 271 out as 1 over 271 squared. And so I'm basically dividing the variance by 271 at the end of the day when we push through that process, that computation that we've done quite a few times. So we should expect that our standard error is considerably less than it was for the sample. And what we're going to find is that the middle 95% of the bootstrap distribution, so 95% of these sample averages lie between 91.9 and 163.23 parts per billion. So 2.5% of the sample averages are below 92, and 2.5% of the sample averages are above 163. And that's 2.5% of like the 10 to the fourth or the 10 to the fifth resamples that we did, okay? All right, so let's go through the R code and see what's happening, or see how it's happening. Okay, so I'm in that chapter 5 file again, and I've got example 5.3 starting on line 50, okay? So line 54 is the first one. What I'm doing here is I guess we could, let's view, and let's view that file. I've got my resample package clicked off. All right, so here we go. We've got arsenic levels, we got chlorine levels, and we got cobalt levels measured. And if we scroll down, apparently we're going to have 271 of these. There it is. Okay, so simple data set. We're only going to look at the arsenic measurements. So line 54 says, all right, I'm going to create a new vector with just the arsenic data in it, and I'm going to call it arsenic, and it's from the Bangladesh file, and I'm just grabbing the arsenic column. Okay. Oh, oops, I don't know why I did that. Let's run that again. I feel good about that. Feel good about that. Don't know what just happened. Okay. Let's look at a histogram of this arsenic data. Let's see how normal it looks. It doesn't look normal at all. Okay, it's got a long right tail. Look, we got some wells way over here past 2,000 parts per billion, and we got a whole bunch of ones right in here. It looks like, well, that's 500. So I don't know what that first column's up to. Maybe 200. So, all right. So we can test for normality by doing a QQ norm plot, throwing in a line, and we see a garbage fit. So this data set is not normal. Okay, well, I'm going to figure out how big my data set is for arsenic. I know it's 271, but if I want to scroll through the data set, I could just calculate its length and display the length of 271. I'm going to run a bootstrap simulation with 10 to the 4 3 samples. And I'm going to create a vector to contain all the bootstrap results, and it's going to be arsenic.mean. All right, so now I'm going to do the loop. So from my arsenic vector, this is line 71, I'm going to sample n, which is 271 with replacement. I'm going to calculate the mean of this resample, the mean of x, and record it in my arsenic mean vector. Run that simulation. There, it's done. I'm going to create a histogram of the means in the bootstrap simulation. So there is the bootstrap distribution histogram, and look, it's pretty normal. Okay, and then I'm going to throw in the line which has the mean of the original data set. The original data set is what we call arsenic. So I'm going to throw in that line into the histogram in blue. You know, I think when I highlight it, it messes it up. So I'm going to rerun line 76, and there's the mean. And if you note, the mean of the original sample, which is in blue, looks like it's about the mean of the bootstrap distribution, which is the histogram. Okay. I can give you some evidence that the bootstrap distribution is approximately normal. QQ normal means that the sample means that I just calculated. There it is. Throw in my line. Don't even see it because, oh, there it is. Basically follows that line except for the edges. I'm going to calculate the mean of my bootstrap distribution, and I get 125.135. I'm going to take the bias, which I haven't defined yet, but it's the mean of the bootstrap distribution minus the mean of the sample. So that's what's happening in line 83. The mean of the bootstrap distribution is mean arsenic.mean. The original sample is arsenic, so I'm going to subtract mean of arsenic, and I get something very close to 0. And there's the standard deviation of 17.86, slightly different than on the board, but pretty much the same. Okay. And then last but not least, I'm going to skip that sum arsenic mean greater than 163 and less than 89.75. Here's line 89 is how we're going to calculate this bootstrap confidence interval. I'm going to take my arsenic mean, that's the vector of all the bootstrap means, and I'm going to grab the interval between 0.025 and 0.975. Okay, so R is going to grab the middle 95 quantile of that distribution. And I get between 92.1 and 163, which is slightly different than I had on the board, but pretty close. Okay, and so that would be another 95% bootstrap confidence interval. All right, so let's go over to the second. By the way, pause and copy if you haven't already. Last panel for this video. Pause and copy. Okay. All right, so formal definition then. The bootstrap percentile confidence interval. So the interval between the 2.5 and 97.5 percentiles of the bootstrap distribution. So you got your distribution, grab where 95% of the probability is right in the middle, 2.5% off to the left, 2.5% off to the right. of a statistic is called the 95% bootstrap confidence interval full for the corresponding parameter. So for us, that parameter was the mean of arsenic for the entire population of wells in Bangladesh. There's more than 271 wells in Bangladesh, so we just had a sample. Now, how do we speak it? We say we are 95% bootstrap confident that the population mean arsenic level is between 91.9 and 163.23 parts per billion. That's what we would say. But what we mean is something quite different. And we're going to reiterate this point, I believe, in chapter 7 when we take a real deep dive on confidence intervals. The true meaning is if I was given a bunch of samples of 271 wells from Bangladesh, and if for each of these samples I bootstrapped them and created a 95% confidence interval, then 95% of those confidence intervals should contain the true population mean. So this is a very subtle point that we'll really get into in chapter 7, but I'm not going to say that there's a 95% chance the true population mean is between 91.9 and 163.23. There isn't. The true population mean is either between those two values or it's not. But what I am saying is if I run this process over and over again with samples of 271, then 95% of the confidence intervals I create should contain the true population mean. Right, so it's a subtle difference, and we'll hammer that home a lot more in chapter 7. Okay. One last note here: confidence intervals don't have to be symmetric about sample mean. So, for example, our sample mean of the 271 wells we were given was about 125.3, and one of our 95% bootstrap confidence intervals went from 91.9 to 163.23. And you'll note that it's 33.4 units between the mean and the lower bound, and 37.9 units between the mean and the upper bound. So it's not a symmetric. It does not have to be symmetric. Now, if the distribution of the arsenic levels in the well was normal, then you would expect a symmetric confidence interval because the normal distribution is utterly symmetric. But our data set, that sample we had, it was not symmetric. It had an enormously skewed right tail, right? Big blob at the left and an enormously skewed right tail. Okay, shut up, next up.